Have you ever wondered what happened in the universe's dark ages, a period shrouded in cosmic mystery? Just as the Earth has its own history, the universe too has a past, a timeline of events that have led to the cosmos we see today. Among the most intriguing chapters of this cosmic history is a period known as the Dark Ages, and the subsequent phase of reionization. Let's take a moment to delve into these fascinating epochs. Imagine, if you will, the universe in its infancy. Following the Big Bang, the universe was a hot, dense soup of particles. As it expanded, it cooled, and eventually atoms began to form. This period, roughly 380,000 years after the Big Bang, marked the end of what we call the recombination era. But what followed was not a universe filled with stars and galaxies as we know it. Instead, it was a time of darkness, a cosmic night that lasted for almost 200 million years. This is the epoch we refer to as the Dark Ages. The Dark Ages were not dark because of the absence of light, but because there were no celestial bodies to emit light we could observe. It was a time when the universe was filled with neutral hydrogen gas that absorbed all the light. And then, something miraculous happened. The first stars, galaxies and quasars began to form, emitting high-energy light that gradually ionized the neutral hydrogen gas. This was the dawn of the Reionization era, a time when the universe transitioned from darkness to light. The Dark Ages and the era of reionization are significant periods in cosmology because they hold the secrets to how the universe evolved from a simple, homogeneous state to the complex, structured cosmos we see today. Despite decades of research, these epochs remain shrouded in mystery, making them a fascinating area of study for cosmologists across the globe. The Dark Ages and reionization, a time of cosmic evolution yet to be fully understood, hold secrets to the universe's formation and evolution. Imagine a universe filled with neutral hydrogen, a time so early that stars and galaxies had not yet formed. This was the Dark Ages of the universe, a period spanning hundreds of millions of years after the Big Bang, but before the first stars began to shine. Now, the term Dark Ages may conjure up images of a universe devoid of all life and light, and in a sense, that's accurate. But don't let the name fool you. Even though it was dark in the sense that there were no stars or galaxies to illuminate the cosmos, this was an incredibly important time in the universe's history. During the Dark Ages, the universe was like a massive, ever-expanding cloud of neutral hydrogen gas. Without sources of light, this period was dark in a literal sense, but it was also dark in a metaphorical sense because our understanding of this era remains limited. We can't see it directly. We can't just point our telescopes back in time and observe what was happening. However, we do have a way to glimpse this period indirectly. This is where the cosmic microwave background radiation, or CMBR, comes into play. This radiation is like a snapshot of the universe at the end of the Dark Ages, providing us with vital clues about the state of the universe during this time. The CMBR is the afterglow of the Big Bang, the oldest light we can see. It gives us a picture of the universe just 380,000 years after the Big Bang, when the universe had cooled enough for the first atoms to form. This light has been traveling through space ever since, stretching and cooling as the universe expands. The data we glean from the CMBR helps us piece together the puzzle of what the universe looked like during the Dark Ages and how it evolved over time. We can use it to understand the distribution of matter, the rate of expansion, and the nature of the dark matter and dark energy that make up most of the universe. And so, the universe transitioned from this dark age, stepping into a period of reionization and light. Picture a universe gradually coming to life as the first stars and galaxies start to form. This is the era of reionization, a period that played a crucial role in shaping the universe as we understand it today. Now, to simplify the concept of reionization, let's think of the universe as a colossal, pitch-black room. Imagine billions of tiny light bulbs. These represent the first stars and galaxies suddenly turning on. You might think the room would instantly light up. But instead, these bulbs are surrounded by a dense fog of neutral hydrogen atoms that absorb their light, keeping the room dark. This is the universe during the cosmic dark ages, with its first stars and galaxies shrouded in a veil of darkness. But this darkness didn't last forever. As these stars burned fiercely and galaxies grew, they started to ionize or charge the surrounding hydrogen atoms. This process of ionization stripped the hydrogen atoms of their electrons, creating a sea of free electrons and positive ions. It was like each tiny light bulb in our room had a powerful fan gradually blowing away the fog around it. As more and more hydrogen atoms were ionized, the universe slowly began to change. The fog of neutral hydrogen cleared, allowing light from the first stars and galaxies to freely travel across the cosmos. The universe, once a dark room, was now transparent to light. This transformation is what we call reionization. But why is this period so significant? Well, reionization wasn't just about turning on the lights. As the universe became transparent, it also began to form structure. Galaxies could now interact with each other, leading to the formation of galaxy clusters and superclusters. In essence, reionization allowed for the universe's structure and diversity we witness today. The era of reionization marked a pivotal point in cosmic history, paving the way for the universe's structure and diversity. But how do we learn about these cosmic epochs that occurred billions of years ago? You might wonder. Well, our cosmic detectives, also known as astronomers and physicists, use a variety of methods to study these periods. One such method involves examining cosmic microwave background radiation, or CMB for short. This radiation is essentially the afterglow of the Big Bang, and it permeates all of space. By studying the tiny fluctuations in the CMB, scientists can glean information about the early universe and the dark ages that followed the Big Bang. Another tool in our cosmic detective kit is the observation of distant quasars. These bright, energetic objects are so far away that their light has taken billions of years to reach us. This means that when we observe a quasar, we're actually seeing it as it was billions of years ago, during the era of reionization. The light from quasars can reveal details about the intergalactic medium it passed through on its journey to us, providing valuable clues about the universe's past. But studying these epochs isn't a walk in the park. The distant past of the universe presents significant challenges. The further back in time we look, the more difficult it becomes to observe and interpret what we're seeing. The light from ancient quasars is extremely faint and often distorted by intervening galaxies and dust clouds. Plus, the early universe was incredibly hot and dense, which can make it difficult to understand the physics at play. And then there's the limitations of our technology. Our most powerful telescopes can only see so far, and even the most sophisticated computer simulations have their limits. But despite these challenges, our cosmic detectives are undeterred. They continue to push the boundaries of what we know, using every tool at their disposal to probe the mysteries of the universe. Through our cosmic detective work, we inch closer to unveiling the secrets of the universe's dark ages and reionization. Each discovery, each clue unraveled, brings us one step closer to understanding our cosmic past and perhaps our future. So, why does uncovering these cosmic mysteries matter to us? Understanding the dark ages and reionization gives us a unique perspective into the evolution of the universe. It's like peering into the past, witnessing the birth of galaxies and tracing the footprints of cosmic evolution. As we delve deeper into these mysteries, we gain insights into the formation of galaxies, the most fundamental building blocks of the universe. The cosmic dark ages and the era of reionization were pivotal moments in cosmic history. They marked the birth of the first stars, the creation of the first galaxies, and the illumination of the universe. By understanding these eras, we can piece together the story of how the universe evolved from a dark, dense state to the vibrant, star-filled cosmos we see today. Moreover, these discoveries shed light on the nature of dark matter. This invisible, mysterious substance makes up about 85% of the universe's mass. By studying how galaxies formed during the reionization era, we can learn more about how dark matter behaves and interacts with normal matter. This could potentially revolutionize our understanding of the universe and the laws of physics. On a more philosophical level, these discoveries help us understand our place in the universe. They remind us that we are part of a vast, complex, and ever-evolving cosmos. We are the result of billions of years of cosmic evolution, of stars being born and dying, of galaxies forming and merging. Understanding the cosmic dark ages and the era of reionization is not just about satisfying our curiosity, it's about connecting with our cosmic roots, appreciating the grandeur of the universe, and gaining a deeper understanding of the laws that govern it. As we unravel the mysteries of the Dark Ages and reionization, we gain a deeper understanding of our cosmic origins, highlighting the beauty and complexity of the universe we inhabit.